let's have a look at some of the ideas we need for excellence level. So when we start off with, we've got our problem, our investigation question, and for excellence we need to make sure that we've got some kind of insightful question. So if, for example, I was rolling a dice, then an achieved or merit level question might be, I wonder what's the chance of getting a 1 on my dice. Whereas for an excellence level question, we need to look at the entire distribution. So I might say, well, when I roll a dice, what's the chance of getting a 1, 2, 3, 4, 5, or 6? All right. So my investigation question would contain all of the outcomes, whereas at achieved or merit level, it might just be the chance of winning or getting a 1 or getting a particular value. In terms of our planning, so when we need to move our plan up to excellence level, we need to think about the conditions that I need to control. And the reason I want to do that is I want it to be fair, the data to be fair and consistent. So for example, if I think about a dice, rolling a dice, I need to think, well, what do I control when I do that? So I can think about, for example, the distance that I am holding the dice above the desk. If I'm just holding it, so if I've got my desk here and I'm just literally holding it, the dice right above the table, versus if I'm holding it way up in the air and dropping it, that's going to give me different results possibly. All right, so I want to control these conditions so that I am consistent. What I would do is in my instructions is I would put a little note, and I've said here I'm going to hold the dice 30 centimetres above the desk. So I'm going to be reasonably precise and try to be consistent. Every time I drop the dice, I'm going to drop it from about that same height. I've also been quite specific that I'm going to release it by having my hand facing downwards and then opening it up so it drops. So I'm being quite specific about my technique that I would use. So these are the kinds of things that I would do. Now I've got a little note down the bottom there. By using the same procedure each time, I am minimizing the variation, which increases my accuracy or my precision of my data. Okay, so that's what I want to think about in terms of the planning, is what conditions do I need to hold constant. Okay, then we have a look at our analysis section. And one of the things that we can do here is look at something called a long run frequency. So this is another type of graph that we're going to draw, which gives us a slightly different view of the data that we have. So as I start collecting more data, I'm getting more and more precise as time goes on. So I want to take this into account with a graph that shows that change in precision. So here is an example, and you can see I've got 2 lines on this graph. And this is just looking at tossing a coin and recording how many heads have occurred. So the light blue line is one trial and the dark blue is a second one. Okay, now what you'll notice is at the start, the first, say 5 trials, you can see that the probability is quite variable. It's moving around quite a bit. Then in the next section, between about 10 and 500 trials, you can see that the variation is getting smaller over time. And as we get up to 5,000, we can see we're getting more and more precise in our estimates. So this is the idea that we just want to explore and be able to draw a graph to represent. So we were just reminding you, if we're tossing a coin, we want to find the chance of getting a head. So we've got to count up how many heads there are divided by how many times the coin has been tossed. So I've got some results here, and I've got from 16 different trials. So the first time I toss a coin, I've got a tail. So how many heads are there so far? There aren't any there. So then the probability of a head is going to be 0 out of, now we've done 1 toss, so 0 out of 1, the probability of that is 0. Now I'm going to do the flip the second time. So I do that again and I get a tail this time. Sorry, a head this time. So that means I have 1 head so far. So I've got 1 head, and so far I've done 2 coin tosses. So the probability, and I'm just going to write this as decimal, is 0.5. Okay, third toss. So now I'm tossing the coin and I get a tail again. So how many heads have I got so far? Still only got one head. But how many times have I tossed the coin? I have tossed the coin 3 times. So as a decimal, 0.333. Okay. Coin toss number 4. I get another tail. How many heads are there so far? There's still only one head. So there's one head out of the 4 coin tosses that I have now done. So that's a chance of 0.25. Toss the coin on my 5th time and I get another head. So now I've got 2 heads in the first 5 tosses. So that's 2 chances out of the 5 coin tosses, and so that is a probability of 0.4. Okay, number 6. I've got a tail, so I haven't got any more heads. I've only got 2 so far, and that's a chance of 2 out of the 6 tosses I've done now, which is the same as 1/3, so that's a probability of 0.333. Number 7, I get a tail, still only 2 heads, 2 out of the 7 ones that I've done, which is a probability of 0.2857. Then number 8 is another tail, so I've still only got 2 heads, and now the chance of that is 2 out of the 8 coin tosses that I've done. So 2 out of 8 is the same as a quarter, which is 0.25. Now the 9th one, I get another head, so now I've got 3 heads so far. So that's the chance of 3 out of the 9 times I've tossed the coin. So that's 1/3, so that's back to a probability of 0.333. The 10th one is a tail, so I've still only got 3 heads, but I have now tossed the coin 10 times. Chance of 0.3. 11th, another head. So now I've got 4 heads out of the 11 times we've tossed the coin. So 4 out of 11 is 0.364. The 12th one, I've got another head. So that means I've got 5 heads so far out of the 12 coin tosses that I have done. And that's a chance of 0.4167. Number 13 is a tail. So I haven't got any more heads, but I have tossed the coin now 13 times. So 5 out of 13 is 0.385. Number 14th toss is a head. So that is now, I've got 6 heads so far out of the 14 times we've tossed the coin. So 6 out of 14 is 0.429. 15 is a tail, so still only 6 heads, 6 out of 15, and that is 0.4. And tossed coin number 16, that's another head, so now I've got 7 heads, so that's 7 out of the 16 times that I've done it, so that's giving me a chance of 0.4375. Okay, so what we want to do now is I've just drawn a graph of those first 10 flips, all right? And so you'll notice that's what I'm plotting a graph as. I'm plotting a graph of these probabilities here versus the number of flips. So this is my x-axis and the probability is my y-axis, all right? So I've got the number of flips on this axis and I've got my probabilities on that axis. And that's what I've done here. So my first one, the probability of a head, the first flip was 0. So that's what I've drawn there, is I put a 0 down there. The second probability was 0.5. So that now coin toss number 2 has a probability of 0.5. Coin toss number 3 is a probability of 0.333. So third one, 0.333 there, and so that's what I've done, is I've just plotted those coordinate points, which is the probabilities, and connect them together with a line. All right, so that's there. And so what you can see in the first 10 tosses is that the lowest probability is down at 0 and the highest is up at 0.5. So that's quite a reasonable variation. That's, from 0 to 50%. So let's have a look as if I do a graph of the first 100 flips. Okay, you've still got your first one there at 0, 50%, and so it's moved around a bit. And we can see as the time goes by, okay, and if I just draw kind of a line hitting these top points and a line hitting these bottom points, what I'm hoping you'll start to see is that at the beginning there's a lot of variation, and as time goes by the amount of variation in the data gets a lot smaller. Alright, now if I extend that out to 500 flips, we can see that that probability there is pretty much around 0.5 or 50%. So that means, that leads us to this idea that the bigger our sample size or the number of trials, the more accurate or precise the probability estimate is going to be. Alright, so that's quite a big idea that I want you guys to take on board.